Now, this time, let's see how to solve a system of equations which has just one solution. The system that we are about to consider is this one, written in the old notation. Now we convert to the matrix vector notation. But how do we do that? Well, the first thing in this conversion from this to this is to put x, y, and z in order. So in the first equation, well, you have x, y, and z in order, so everything is fine. So I write here the coefficients 1, 1 minus 1, here 1, 1 minus 1, and the right hand side 1 is written here. For the second equation, I have here 2x, the coefficient is 2, minus y, the coefficient is minus 1, and 2z, the coefficient is 2. So it's the 2 minus 1 and 2 that you find here. On the right hand side, we have the 9 here. On the last equation, however, notice we do not have the variables in order, so you must put it in order. How? Let's see, just rearrange, right? You just rearrange this. So we have x and z to the other side, so we have x plus 2y minus z is equal to 0. Now the coefficients are 1, 2, and minus 1. 1, 2, minus 1 that you find here. And the right hand side is 0 here. So the conversion is done. Now let's suppress the x, y, z column here, because we do not need it during the elimination process. And instead, we just append this column to the matrix that you find here, and we get the augmented matrix version of the system that you have here. And this is the object we are going to work with. It's on this augmented matrix that we are going to use the elimination steps. So what are these steps? Well, we first identify on the first equation the first entry, and this entry is called the pivot variable. It is a pivot entry, and our goal is to use it to eliminate the entries downstairs, the 2 and 1. Now, in order to eliminate the 2x entry on the second equation, I'm going to multiply the first equation by minus 2 and then add that equation to the equation below. This is what I wrote here. The new L2 prime equation is the old L2 equation minus 2 times the first equation that you find here. In doing that, well, let me write it. If I write it, you can see it. So you have the second equation is 2x minus y plus 2z is equal to 9. But now on top of this, I'm going to add minus 2x minus 2i plus 2z, and on the right side, I'm going to add minus 2. Can you see? You just sum everything. So this is the first equation multiplied by minus 2, and I'm going to add it to the left-hand side of the L2 equation, the second equation. If I do that, notice these 2x cancel, and the result is a 0 coefficient here. Now I just compute the consequences of this elimination. Namely, I must add minus 2y with minus y, which gives me the minus 3 here. And finally, the 2z sums with 2z, which gives you the 4z here. And 9 minus 2 is 7 here. So again, we just focus on the pivot here. We try to eliminate the corresponding entry below. We do that by multiplying the first equation by the appropriate number, in this case minus 2. And now we sum that equation with the equation below. In the process, that entry here that was before 2 now is eliminated. It turns into 0. That's it, the idea of elimination. Now we just repeat the process and use this pivot to eliminate the 1 on the third equation. To do that, I'm going to multiply the first equation by minus 1 and then add it to the last equation. This is what I wrote here. The new L3 equation, L3 prime, is equal to the old L3 minus the L1 equation. Well, let's do the calculation. 1 minus 1, well, it's 0. 2 minus 1 is 1. Minus 1 minus 1 gives you 0, because the minus cancel. And finally, 0 minus 1 is minus 1. So you see now that below that pivot, we just eliminated the 2 and 1 coefficients that were multiplying before the x variable, which means that in this system, I no longer have the x entry here and the x entry on this last equation. I just eliminated the x from these two. Now let's keep moving, and I wish I had the 1 here, so I'm going to flip these last two equations. So L2 switches with L3. 1, 0, 1, 0 now becomes the second equation, 0, 1, 0, fine. And, well, our goal this time is to use the second pivot here. This is the first pivot that we use. Now let's use the second pivot to eliminate the variables downstairs, in this case, the variable y. How am I going to do that? Well, I'm going to multiply this equation, the L2 equation, by the appropriate number. This term, it is 3, because if I multiply this equation by 3, I get here a 3, and when I sum this with a minus 3, I get the 0. Of course, 4 plus 0 gives you the 4, but 7 plus minus 3, can you see? Gives you the 4 here. Just sum both equations. Finally, I wish I had here, see, we have 4z is equal to 4. Let's divide everything by 4. You get z is equal to 1. Fine. At this system, we can see 3 pivots, 1, 2, and 3. And finally, after I eliminate everything below the pivots, let's try to eliminate above the pivots. What variables are above the pivots? Well, for example, the minus 1 here. How am I going to eliminate this minus 1? It's easy. I just sum this last equation with the first equation. This is what I wrote here. And the minus 1 with the 1 gives you the 0. Everything is fine. 0 plus 1 keeps the 1. 0 plus 1 keeps the 1. But notice, the 1 plus 1 gives me the 2 here. Always pay attention to this left-hand side. Finally, there is still one more variable to eliminate here, the 1. How am I going to do that? Well, it's written here. The new L1 equation is equal to the old minus the second. Because if I do that, well, you get 1 minus 1, which is a 0 here. Of course, 2 minus 1 is 2 plus 1, which is a 3 here. And finally, we arrive at this simplified, super simplified system of equations. It's just 1s on the diagonal and 0 below and 0 above. It's easy to read the solution from this system, because the solution must be x is equal to 3, y is equal to minus 1, and z is equal to 1. This is the answer to the question, when we have the identity. So the idea of the elimination process is to use these pivots to eliminate as much as possible everything down and then up. And as a result, get closer and closer to an identity matrix. A matrix with 1s on the diagonal and 0 everywhere else. Now let's make an important observation regarding this system. How many pivots are there? Let's call it R. How many pivots are there? There are 3 here. 1, 2, and 3. How many pivots are there in the augmented matrix? There is 1, 2, and 3. This column does not add a new pivot. Maybe it's useful to think about the columns where the pivots are independent columns. So notice that this column is independent from this column and from this column. There is no way I can create one from the other. But this fourth column can be constructed from the other three, and therefore is a dependent column. Therefore, it does not count. There is only 3 independent columns in this augmented matrix. 3 again. There is no 4, just 3. Finally, how many columns are there in the matrix? The matrix has 3 columns. In fact, it's 3 by 3 here. And now I'm going to make a claim that we are going only to justify later. The claim is AX is equal to B as one solution if R is equal to R star, which is equal to N. It happens here. R is equal to 3, R star is equal to 3, and N is equal to 3. All the same, as a consequence, AX is equal to B only has one solution.